Hello ladies and gentlemen, welcome back to another video of the Elders Morph. Now I understand I haven't made Universe Sandbox 2 fictional solar system videos or other types of videos like that, but I've just had one of my subscribers called Maximilian Freedom, and he's kind of woken me up to the fact that he loves these videos. He enjoys them, and he's even said that my other subscribers seem to enjoy them. So he's asked me to see if any of the planets in the Trappist 1 system can have a moon. Or a couple moons, and see if the system stabilizes. So the first planet we're going to look at is Trappist 1H, because why not? Trappist 1H is surprisingly a small planet, to be honest. I didn't expect it to be this small. It's only 40% the size of the Earth, so what we're going to do is we're going to slow down everything, and we're going to get a small moon, or should we get a large moon? I don't know. Let's get a large moon, and let's just stick it in orbit. Let's speed up time, see if it stays in orbit. It looks like it is. Looks like it actually is going to stay in orbit. Okay. Oh, this is a bigger planet. Trappist 1G. Now we all know about Gliese 581G and how the planet is fictional. Meant to be the best candidate for Earth life. So what we're gonna do is gonna plot moon here in orbit. Are you gonna stay in orbit? Yeah, it looks like it. So we got two moons now around a red dwarf. These just let me get the sun. Right, this is the sun. Let it load. Right, look at the sun. Right. Guess where Mercury is? Yeah. Yeah. So these planets are really fucking good. Let's go to let's go to this planet. Small moon in orbit around here. Oh my god. Oh, hang on. Oh. No. Oh, hang on. Is he gonna say no? Not by the looks of it. He's gonna smack the planet. There you go. Alright, so the first planet can't support a moon. Now, can Trappist 1C hold a moon? Let's have a look. Oh, it's kind of fighting against the star. Is it holding it? It is holding it. That close? Really? So that means that that doesn't make sense. So what you have if you have a planet, of course it's 1.38 times the mass of the Earth, but it's still about the same size as the Earth. It's holding a moon twice the size of our moon around a red dwarf, a ultra cool red dwarf, the smallest kind of red dwarf. This is just wow. This is crazy. This is just absolutely crazy. So this shows that you can indeed have moons around planets around the red dwarf. So what we're going to do is we're going to go out a planet further to Trappist 1D. Now this planet doesn't have a bloody atmosphere, so we're going to give it a bloody atmosphere. There you go. And we're going to make sure its temperature stabilizes. There you go. We're going to give it a moon. Because why not? Oh, that's a big ass moon. Oh, dear God, Jesus Christ. Give it a moon. It's a massive moon. It's, well, I mean, it's not that big. That's huge. Oh, triple solar eclipse. That was amazing. Triple, absolutely beautiful. Stunningly beautiful triple solar eclipse. Wish they put a feature in where you can reverse time. I'm not sure if they have put a feature. Well, it is, we're gonna get the largest moon that's here, and we're gonna stick in orbit. Because why not? That's what we do, isn't it? Is that gonna stay in orbit? Bloody hell, by the looks of it, it is staying in orbit. So if we raise this up to about... Oh, look at that. So yeah, we are 1, 2, 3, 4. 4 moons in this system already, and this system is still staying. This is just stupid. This is... Maximilian, if you're watching this, then just don't, just make sure you hold your jaw, because this is amazing. A planet this close can hold a moon? That is amazing. So we're going to go to the 5th planet. Well, Trappist 1F, whatever you want to call it. This is a very large planet. I don't know why it's so large. Oh, it's got ice on it, that's right. We just get a planet instead. No. No. Oh, I want a large enough moon. So the right size for a moon. And that is definitely staying on orbit. Hang on, let's have a look. Let's have a look. Oh. Oh. One there, and one there. They're not touching, are they? Not by the looks of it. Oh, shit. That's not going to work. Are these guys staying in orbit? By the looks of it, they are staying in orbit. Oh my god. Oh no! Alright. This has 3 moves now. That moon is getting awfully close. Actually, no, it's not. Not getting that close. One, 2, 3, 4, 5, 6 moons. 5 moons. 3 moons now. So yeah. Oh, what on earth has happened there? 2 moons now. That moon is literally scraping the surface of that planet. That is just stupid. So, did he ask me to fuck up the system? Let's have a look. Oh, excuse me. And see when the system restabilizes. Yeah, Maximilian, you got a bit of a problem there. I mean, the system, it didn't even destabilize. It's staying as it is. This is quite something. This is just, I'm daring not to speed up time because I don't want to fuck up the system. Because this is such a beautiful system. I mean, you've got, one, two, three, you got 4 planets, 4 bloody planets in this habitable zone of this red dwarf. This is just stupid. Just to give you, just to show you how close these planets are. You can quite comfortably see this planet. You sit on this planet, you can see that planet in the night sky, in the day sky or whatever. That just shows you how close these planets can really get to each other without destabilizing each other. And Trappist 1 is only 83.8 mass Jupiters. But I believe it is slightly smaller in radius. No, it's bigger. But not by much. Bloody hell, not by much. So this is basically a Jupiter on steroids. Think of this one. Hang on, let's look. Okay, I'm officially done. What the fuck? What the hell? That doesn't make sense. So Jupiter is 83.8 times less massive than this star, yet it can hold on to more objects. Or is it just that we've seen these 5 planets and yet we haven't even seen, like, I don't know, probably a couple of gas giants out in the system, like probably 4 gas giants. Maybe that's the case, and probably there's a planet on elliptical orbit like that, or maybe a couple, or something like that. We just do not know, unless there is like a massive belt of objects, like you know the Oort cloud. Fucking moustache. You know the Oort cloud. That blocks out some of our light from our star. It could be the same with Trappist 1. It could be blocking out the light from the gas giants. Now, no, I'm not going to rename all these bloody planets because these are fictional. Right, these are bloody fictional planets. Right, the real planets are here, the Trappist planets. These are fictional planets I've just put in. I'm not gonna rename them because then I will be upsetting a lot of people, including NASA, and I do not want to be in NASA's bad books. Now, oh! All those planets were lined up. That was, what the fuck? They were all lined up. That is just, oh my god. So, this system, if you are on Trappist 1H, right, so if you are like why are you calling now faster? Alright, let's just screw physics. 18 degrees, there you go. So if you're on Trappist 1, Trappist 1H, You're getting a solar eclipse probably every couple minutes. There you go, there you go. 2 solar eclipses. Alright, so this is just stupid. Like, this shows us that the chance of life being in the system, and I know that Anton has already said that the system is a very weird system. It's the star. The star is something like 459 million years old. Now I know that most of you could be saying, "Oh, that's really old for a star." For a red dwarf, it's not. For a red dwarf, that's still basically in its baby stages. It's still a toddler. While our sun is basically an adult. It's an adult star. It's like a. The star is just. And also, just talking about this, it's not that active at all. And that is odd. So what we're going to do is we're going to look at its magnetic field, and it doesn't even have a magnetic field. Now, because red dwarfs are supposedly, hypothetically, more active than sun-like stars, you would expect the magnetic field to be huge. Like something like that. And I know it doesn't show up, but for example, that will be it's not even can't move the magnetic field. Holy bollocks! That's a big magnetic field. Bloody hell! Oh. Okay. The magnetic field is decreasing. This is really odd. The magnetic field is decreasing in power. What? How does that make sense? Oh, mass loss. Hang on. The planet's losing mass. So that means that the magnetic field will drop in power. So go back to Trappist 1. And oh my god, how big is this magnetic field? I don't know how big this magnetic field is. Here, let's go down in power again. There you go. Is that the maximum we could zoom out? So the Trappist 1 system magnetic field will not be this big. Okay, so don't panic. It won't be this big, because if it was this big, it would probably span the entire Trappist 1 system, and I can't zoom in. Oh. There you go. Probably the star's heliosphere will probably span about here, maybe. Now forget the comet-like structure. It'll be like well, it would be like a comet, but it won't be moving like this. It will just be stationary. I mean, the star is going to be orbiting the center of the Milky Way, but very slowly. So, in fact, this comet-like structure will spin around. Will change very slowly, and we're not really sure. So what we're going to do is we're going to go to the magnetic field because we don't know. So what? Now, if it's true and these planets do, obviously they orbit this close, but they do. The star's gravitational pull should be enough to pull and push on their cores. This meaning their cores will be incredibly active, and they'll all have magnetic fields. So, what we're gonna do is we'll give them magnetic fields because we can. And so they'll all have magnetic fields like this. But what's really confusing is that, well, it's not really confusing in a way. It's like, how do I say it? It's like, the star is confusing. Well, everything about the place is so is confusing. So what you have is you have a baby star, very young red dwarf, with planets around it. Bearing in mind that that's decreasing. Density's increase. Anyway, so this star, Anton, if I get this right, Anton said that the star, red dwarfs are incredibly active, and that they are. But what I think he missed is that because red dwarf planets orbit so close, the gravitational pull from the star will, yes, tightly lock them, but also it will pull and it will crush the core. So you know when you hold a sponge ball and you crush it and you squeeze it and pull on it, red dwarf stars will do that to their planets. So what this means is that these planets most likely will have a magnetic field, most likely will have an atmosphere, most likely will have water. Life, I would say about 30-70. So 30 yes, 30% yes, 70% no. So chance of life is no. We could live on these planets. That's if we live on the twilight zone of the planet. But yes, we can live on these planets. No I'm saying about it. Now, I'm not saying that Anton is a bad person. What I am saying is that I think he's missed out that part where about the tidal friction of the star having a massive gravitational influence on the planets. Now, obviously, Trappist 1H could be slightly too far away from the star, and yes, I have changed the planet's characteristics because of reasons. But it might have a weak magnetic field, like a pretty weak one, so probably one that looks like well, probably not weak, but not strong. Probably about as strong as Earth. So, yeah, probably about this strong. I mean, even the moons will have magnetic fields that will that will the moons will have magnetic fields. So they'll probably be about this powerful. So every object in this system will probably have a magnetic field. Like even the asteroids, if there are any asteroids in the system, they will have weak magnetic fields because of all the charged particles and the gravitational pull and everything coming off of the star, crashing into the planets, exciting the magnetic field, and you have aurora borealis all the time. Now, I know that sounds a bit stupid, but that's a red dwarf for you. A red dwarf will a red dwarf, right? The sun is like a battery. A red dwarf is like a battery on super steroids. It's going to supercharge magnetic fields. Now, I know that some of you, and including the people that believe the Earth is flat, are going to say, no, they don't. Solar wind does not charge up a magnetic field. It kind of does, because if you look at, for example, put our sun, for an example, right? You could, when you get a aurora borealis, that's kind of like the sun charging up the magnetic field of the Earth. But also, I mean, it doesn't weaken the magnetic field, but it doesn't really it doesn't like strengthen it in a way, but it does replenish it. So without a star, the magnetic field up is, so say a rogue planet, right? So if we get a new system, just a new simulation. So basically, if you have a rogue planet, and that planet is alone because it's called a rogue planet, over time its magnetic field will decrease in power. But if that rogue planet comes in contact with a star and it gets snatched up by the star, so it starts orbiting the star, probably in an elliptical orbit or whatever, the solar wind from the star will start to replenish the magnetic field. So red dwarf planets, their magnetic field will never, ever, ever decrease in power. So for an example, if we get a gas giant, right, if we get a gas giant and make it very big, like 9 times the mass of Jupiter, right, this will probably have a very, very strong magnetic field, probably about 45. I said 45. Anyway. So we're gonna stick you there. We're gonna stop you, and so you have a rogue planet like this, and I know that starts there, but I put the star there so I could show you the magnetic field. So you have a rogue planet with a magnetic field, right, probably about this big. Over time, it will decrease in power. It will get smaller and smaller and smaller. It will speed up, decreasing. But if it comes in contact with a star, for an example, a red dwarf, So if we pull this red dwarf close to star, then okay. If we put it a little bit closer, because it's not really doing anything. So over time, the decreasing of the magnetic field will slow down. Once it stopped decreasing, the solar wind from the star will funnel down into the polar openings of the magnetic field, and the magnetic field will start to get replenished to its original size. It will never ever be bigger than it is. It will always stay at its original size, right? So don't get confused. Red dwarfs will be incredibly good for fixing or healing planetary magnetic fields. Like for example, if we get rid of this, if we stuck our moon in orbit, right, around here, okay, our moon used to have when our moon first formed, it had a magnetic field, right? So it had a pretty strong magnetic field. So it looked something like this in a way. So because our moon has a pretty weak magnetic field, it has a magnetic field incredibly weak like this. Over time, the solar wind would replenish that magnetic field so it comes back up to its strength, and so the moon would have a magnetic field again. This happens with every star, obviously except from blue supergiants, because they die too quickly. But red dwarfs, sun-like stars, white stars like A class, G class, K class, M class, even brown dwarfs will be able to fix planetary magnetic fields. Now I know that brown dwarfs aren't actually stars; they don't give off heat. But if you have a brown dwarf on the edge of becoming a star, so it's all it needs is just an asteroid to hit it and it just turns into a star. It's going to be giving off a huge amount of heat that will be incredibly close to the heat that's given off by a red dwarf. And once that brown dwarf turns into a star, so brown dwarf, once that brown dwarf turns into a star, it might take a few it might take a few hours or probably a few minutes. Well, yeah, a few minutes for that solar wind to hit the planet. But if that planet has even if that planet only has to have an incredibly weak magnetic field, that solar wind will, over time, start to replenish that magnetic field. Now, going back to the Trappist 1 system that Maximilian asked for. Sorry for backing out of it, Maximilian, but I don't know why I wanted to put this on to the subject. But yes, the chance of the planets being habitable around the Trappist 1 star is incredibly high, because for one, the planets are incredibly close to the mother star, and the star will be creating a massive gravitational influence on the planet. The star will be almost like massaging the cores of the planets, meaning that the cores will stay nice and hot. They will create a magnetic field, and the solar wind coming off the Trappist 1 will keep her planet's magnetic fields stable, so their magnetic fields will never deplete, because for one,